All right, last time we were looking at example of using airplane A. And we were plugging in numbers into the solution equations down below. The other way to do this is to solve this matrix problem numerically. So I'm going to show you what that looks like today. And as long as you have a computer or a calculator that can solve a 2x2 matrix, this is a lot easier. Remember what it took to plug all the numbers into the formula. So there's the matrix. Oh, let me put this on the screen for you. So we're just filling in the numbers from the tables on this. They make it bigger. There we go. So you still have to calculate this ratio here, but it doesn't show up a bunch of different times in the calculation. And so you can plug this in to MATLAB and call this like an A matrix, call this a B matrix, and solve as fast as you can type in the commands. We get the same numbers that we got last time after a lot of effort. So here's the MATLAB solution. Here's the numbers that you get. And I'll show you the MATLAB commands just to remind you how to solve this in MATLAB. But these are the same values we got last time. So in MATLAB, you say A equals, and then you enter it as a matrix, which is row, return, row, close bracket. And then it spits back A. And I checked the determinant just to check the value that we calculated last time, because that's the denominator of those solutions for alpha and elevator. Per Kramer's rule, the determinant is in the denominator. Also wanted to check our calculations that we did last time. And then B, for n equal 1, B is 0, and you get minus 0.04. And you get these values in degrees. And the way you solve it is you do A matrix backslash B. You can also write inverse of A times B. Both work. They say this is faster because it uses Gaussian elimination and it doesn't have to find the whole inverse. I always have difficulty remembering this. In fact, I was just writing code and I wrote it B backslash A and it did not work. Seems like it ought to be B somehow weirdly divided by A, right? Because you're solving AX equal B. I think they do this because when you solve it, you actually pre-multiply by the inverse, right? So A inverse times A gives you identity, and then you get A inverse on the right-hand side. So this is how you solve. And then if you plug in n equal to 2, you get a different right-hand side. The A matrix stays the same, and you get the solution that I showed you and that we got last time. All right, again, we notice that the elevator goes from positive look at the lag there. Positive, trailing edge down, to negative, trailing edge up. And we talked about that since the lift acts behind the CG. More lift to pull the G's causes a nose down pitching moment. So we need to counter with an elevator that produces a nose up pitching moment. This is actually an important parameter that we want to calculate, is how much elevator changes with load factor, because it's feedback to the pilot. The pilot has to move the elevator to a new position to pull G's, and that gives him feedback as to how much he's stressing the airplane and the airframe. So that's the next thing we want to talk about. So we want the change in elevator per change in load factor to be negative, because that's what we saw. And that means the pilot has to pull on the stick. So that means it goes from trailing edge down, which is positive, to trailing edge up, which is negative. This is the elevator I'm drawing. And so you get that negative elevator per G. And this is linked to the stick moving backward, or this is load factor equal 1, load factor equal to 2. How do we know that? It's because to pitch the airplane up, you pull on the stick, and you do that by making the elevator go up. That's the mechanical connection. Forget pulling G's. If you want to pitch the airplane up, you pull on the stick. That's the way it's geared. And pulling on the stick pushes the elevator up, which pitches the tail down and the nose up. So you get a positive pitching moment from this movement. So elevator going from positive to negative pitches the aircraft up. And this feels natural to the pilot, because when he pulls on the stick and pitches up, he tilts back. It fits, right? And if he's pulling G's, it feels like he's being pushed into the seat, and he's pulling on the stick to make that happen. So we want to take the derivative of our elevator solution with respect to load factor to get this value. So let's jump back to that formula. So that's why the formula is nice as opposed to the matrix, because how do you take the derivative of the matrix? You don't. At least I don't know how. Maybe the math guys could tell us that, but we have to take the derivative with respect to the unknown in the matrix problem. But from this formula here, we can take the derivative with respect to n. N shows up here and here, so we're going to get a 1 plus 1 over n squared, because this is n to the minus 1. And then the n here, the derivative of this with respect to n just gives CL trim, and then everything else gets knocked out, so it's real nice. So imprint this in your brain, or you have it written down in your notes, right, or in your book. So we're going to take the derivative of that on the board. And that's going to give us elevator per G. So questions about the stick being pulled back to pull G's. Either the gearing to the elevator or the fact that the elevator changes positive to negative or any of that, because that's an important concept that's sometimes hard to remember or hard to connect, because you've got to remember how the stick is mechanically connected to the elevator. And then you got to remember how the elevator wants to change to pull G's. If you're a pilot, this is in your brain already, but if you're not, you have to remember that. So I guess everybody should be required to be a pilot, huh? $8,000 later, you've got the prerequisite to take this class. It'd be nice. It'd be even nicer if your tuition paid for that. But we're not Harvard or Yale, where you pay $60,000 a year to go to school. And they do that kind of thing. A friend, a teacher, maybe you guys have had Dr. Behrman for physics, in physics. Her daughter went to Harvard. She was a national merit finalist, so she got all these scholarships. And they took English literature her freshman year. Have I told you this? English literature her freshman year, at the end of the semester, the teacher said, oh, by the way, the last week of class, we're going to England to see the places we've been studying. Paid for by the university. What a sweet deal, huh? Of course, it costs $60,000 a year to go to school there. All right, so let's take this derivative. So this is that first term I was showing you. By the way, her daughter got a PhD in the history of science and is now, I believe, at Johns Hopkins. So that's the derivative. Oh, we haven't said this yet. Forget that zero. All we did was take the derivative. So far, so good. And CM alpha, we have a nice formula for that in terms of CL alpha. So that's going to help us out when we do move forward. So remember, long time back, in fact, this was a homework problem. You showed that this is true. There's the CG location, there's the aerodynamic center of the airplane. And so you punch in the numbers here. Either you punch in CM alpha or you punch in the CG and aerodynamic center location, and you can calculate elevator per G. And as long as it's negative and it's sufficiently negative, you get proper feedback. So as long as this is less than 0, you get good feedback because of all the reasons we talked about. So then you might ask, well, what would mean bad feedback, or what would cause bad feedback? And we look at it, and we can't change the gravity. Looks like things change a little bit with flight speed U1. CL alpha and CMQ are in here, so those are stability parameters. And here's CM alpha. We know CM alpha is a huge pitch stability parameter, right? Then we look at CM alpha and we go, oh, maybe if we change the CG enough, this could go 0 or maybe even positive, and we'd get bad feedback. And that's the most likely thing. Once you build the airplane, everything else is fixed. And so you design the airplane so that with good CG positions, you get negative values for this. But then what happens if you load the airplane Where's a bad CG position? We already know one bad CG position, right? It's if the CG is at the aerodynamic center or neutral point, you get 0 pitch stability. So this is another case that we can check. We can set this to 0 and find out the CG location. That's called the maneuver point. It's the bad CG position that makes it difficult for pilots to maneuver the aircraft because they don't get any good feedback. And so let's write that definition up here. Well, let's put it below here. So that's good feedback. When this is 0, we get the maneuver point, which is a CG location giving the derivative of elevator with respect to G equals 0. So you get no feedback. And if you get further beyond that point, then you get the wrong feedback. So we just solve for this. So that's equal to 0. And you can knock out the CL alphas here because you can factor that out. The denominator we don't care about because we multiply both sides by that and knock that out. And we can easily solve for the maneuver point location that makes this 0, right? All I'm going to do is plug this in here and do algebra to isolate that on the left side. So just like the neutral point of the aircraft, we get another CG position and on this X bar AC, I like to put of the aircraft so that I remember that that's not the AC of the wing or the tail. Let's see, where was I? CMQ. The nice thing about this is if we have a stable airplane, one of the things that we said we got was that this is negative. Meaning if the airplane starts to pitch up, nose up, the horizontal tail sweeps downward and it's going to stop that motion. So we get a pitching moment of that horizontal tail sweeping downward, we get a force upward that tends to stop that pitching motion. So if we have a stable airplane, this is negative. So we have a minus sign and a minus sign here. CL is positive. Gravity better be positive. All of this is positive. And so it means that the maneuver point for a stable airplane is behind the aerodynamic center or the neutral point. So that means as long as we get pitch stability by making CM alpha negative, and that's sufficient, then we also get maneuver point stability or maneuver point feedback. But it's important to calculate this for our airplane because we want to make sure we get sufficient feedback for the pilot. So that's the longitudinal trim for a turn. Now we need to do lateral directional trim. We set up the problem before, and we solved it. You remember the deltas. Let me pull that up. Remember way back here, we set up this lateral directional trim problem. Complicated, right? It's in terms of bank angle, and the bank angle got in there because of P and R. Sorry, Q and R. And then we had solutions here using Cramer's rule that look like a nightmare to calculate. So we're not going to do this. We're going to just use this matrix problem. We're going to plug the numbers in here for airplane A. So I'm going to write that on the tablet. I think it might be easier to see on there, I hope. So let me switch to sharing from there. So remember this. Get that memorized, right? You're just going to have to trust me that I'm grabbing the right numbers from the back of the book. All right, here's our big canvas. And we're doing this again for a load factor of 2. And so load factor is equal to 1 over the cosine of the bank angle. So if you plug in 2 for n, you find out the inverse cosine, the bank angle, is 60 degrees. It's a pretty steep bank, even for a load factor of 2. If you're in a commercial airplane and they bank to 60 degrees, you feel like something's going wrong. Usually means that they've lined up with the runway, and then for some reason they have to do a go around, and they have to turn and come around, although typically you don't see much over 45 degrees. All right, so here's our matrix. There's our unknowns. Remember, these came from the lateral directional equations. And the numbers that go in here are from the appendix in the back of the book. This is airplane A. Yeah. Yeah, how did you catch that? Good job. I left off at 3 there. Let me fix that. Eraser. So that's, you must be looking at the back of the book, at the appendix. Yeah, thanks for double checking. The other ones look like they're good. And then the right-hand side, we've got to plug in a whole bunch of stuff. So I'm going to give you the results of that. So this is where you plug in the bank angle phi and do those sines and cosines and sine squareds, calculate a bunch of stuff. So you can write these results down and then try it at home if you have time. And then we, as again, solve on MATLAB. So this becomes the A matrix, and this becomes the B matrix, and we plug in the solution. And we get beta is minus 0.0018 radians or minus 0.1033 degrees. This is steady state, so put a 1 on there, aileron. And so the main effect is that we need a small amount of rudder. So why do we need the small amount of rudder? It's because we have a yaw rate R1 that goes into the equations, and that yaw rate coupled with CNR, remember that term? It's the yawing motion due to yaw rate, so that creates a yawing moment, and you need the rudder CN delta R to counter that. It's not a lot, is it? It's about 1 degree of rudder. And you need just a tiny bit of ailerons, and beta turns out to be small. And so this is the reason why a lot of people argue that a coordinated turn means small beta, but that's not true, especially if we go into like a fighter airplane where we're not doing 2G turn, we're doing a 7G turn. Then you need quite a bit of rudder, and you do get significant beta, and you do need ailerons to stay into that turn, because you're doing that knife edge turn that you see in the air shows when you watch the Thunderbirds. So this is the lateral directional part of the steady state turn. Obviously the longitudinal part is much more important, but you need to show that your airplane can trim lateral directionally for the turn, and if you're doing a high G turn, you will need to show that you have enough rudder and aileron, and you don't get such significant beta that it causes problems in the turn. So that's the story of maneuvering or turning flight. I do want to wrap up a few things about the turning flight. So I'm going to do those on the board. I'm going to have you draw a picture. So let me shut down the screen share here. And before we jump to that, let me show you that solution. in MATLAB, just so you can see the steps and remind yourself how you do that. So this is the A matrix that we just wrote on the board. No, I wrote on the notepad. And there's the B matrix, the right-hand side that we calculated. And here I did inverse of A times B. I could have done A backslash B. And then you get the radian solution. And multiply by pi, 180 over pi, and then you get the degree solution. So those are the numbers. So this is literally how you would do it in MATLAB. You guys probably all have calculators where you could do this as well, right? Again, most of the time, if you just want number calculations, you'll solve the matrix problem. But if we're doing like elevator per G, it's nice to have the actual formula where you can take the derivative of to get those calculations. All right, 5 more minutes and we'll wrap this up and you can go home or wherever you're going to go. So we're going to draw another picture. I want you to copy this down. It's our airplane banked again. It's similar to the one that we already did, but it doesn't hurt to draw it again. And we're just going to isolate a few of the forces again. And this has to do with the physics of turning flight. But some of it, we might as well just talk about circular motion. Because what we have is an airplane that is a mass following a curved path, and we can calculate the centripetal acting force. So big picture of our airplane with some cool looking wings. There we go. Throw in a vertical tail. Right on here, aft view, so we know we're looking from the bottom, not the bottom, the back, which means this is a positive bank angle. Why? Because the x-axis is into the board. Right-hand rule says that that's how we define positive phi. Free body diagram, weight acts down because that's just life on our planet Earth. Lift acts perpendicular to V infinity, perpendicular to the wing. Why is that? Because that's how we all define lift. We want to break that into components, vertical and horizontal, because the vertical component is going to counteract the weight, and the horizontal component is going to provide the centripetal acting force that causes this thing to rotate around the Earth-fixed z-axis with a turn rate of psi dot. Again, we've drawn a lot of this picture before. We're going to recap here. So the radius of the turn is this. The airplane's swinging around the axis of turning. And these components, this is the bank angle phi, so this is L1 sine phi, this is L1 cosine phi. And the centripetal force that we need, because we just know this from experiment and from Sir Isaac Newton and everybody else, is mv squared over the radius. And we need to do a little bit of circles here. We know that a circle, the arc length, traversed by our airplane or anything else following a circular path, the arc length S is the angle psi times the radius, right? You go through part of a circle, the arc length is the subtended angle times the radius. That's just the definition of radians. 2 pi radians is all the way around, and that gives you this circumference, right? So then if you take the derivative of this, the velocity is ds by dt. So that's d psi by dt times RT, and then there's our turn rate, psi dot. So the velocity going around the circle generates the psi dot at the radius RT. Obviously, the further you are out at the same turn rate, you're going faster because you're further out. So if we do a force balance in the horizontal direction, we find out that L1 sine of phi has to be equal to m u1 squared over RT. But we notice from over here, U1 is psi dot RT, so we can plug that in for one of the U1s and get this in terms of M U1 psi dot. All right, so hang on to that. And then if we look in the vertical direction, let's see, vertical, we got L1 cosine phi is equal to the weight, or mg. And in fact, that's where we defined load factor, right? We said lift over weight is 1 over cosine phi, and that's what we called load factor. So it comes directly from that vertical direction force balance. But now I want to take, let's say I want to take this equation and divide it by that one. And again, this has nothing to do with aerodynamics or anything. This is just the physics of this thing going in a circle. So if I do that division, I get the L1s cancel out. I get sine over cosine, which is tangent. And the masses cancel out. So I get U1 squared over G RT. Did I do that right? Or if I solve for RT, up there, I get U1 squared over G tangent phi. And this is where I wanted to get to. If we increase the bank angle, what happens to our turn radius? Assuming we keep the velocity the same. So bank angle goes up. This becomes bigger, right? Tangent becomes bigger. So the turn radius goes down. It means we're doing a tighter turn. And that's just circular motion. If you increase the centripetal force, you can do a tighter turn. So for this airplane, the bank angle is generating that centripetal force. So the higher the bank angle, the tighter the turn. And then how about we flip things around? If we keep the same bank angle and we increase the velocity, what does that do? Means the turn radius goes, let's see, this this turn radius goes up, right? And it goes up with the square of the velocity. So the faster you go at the same bank angle, the wider the turn you have to go. It's the same deal when you're driving your car, right? At a really high speed on the interstate, you can't do a really tight turn because the tires are providing that centripetal force, and they'll break free from the pavement and you'll go into a skid if you try to do too tight of a turn. And that's one of the major reasons for variable assist power, rack and pinion power steering, is that it increases the wheel force in your car when you're at high speed so that you don't over G your car and skid out on the turn. You can still do it, you just have to push harder on it. So that's feedback to you as the pilot. So this is airplane related with regard to the bank angle, but everything else is just normal circular motion that you did in physics and dynamics. All right, so that wraps up turning flight, and we'll call it good for the day. You're working on a new homework set, which is due next Tuesday. No, that's not right. Yes, that's right. Next Tuesday, right? Then you're doing this in MATLAB. Anybody having issues? I've got a couple emails about people trying to get licenses over here, either remote logging in, and it turned out that some of them were checked out already, and they had to try later. Anybody? Is that mainly because you have MATLAB at home, but you don't have Simulink? Is that what I'm remembering? At different times, yeah. These assignments don't need Simulink, so typically your student version is just fine, or whatever the free MATLAB version is.